netspooky, you can take it away.
Hell yeah, awesome.
Hell yeah.
And thanks y'all for everything. So yeah, this is my talk. This is called Adventures in Binary Golf. So if you've seen some of the stuff that I've done, well, I'm gonna power off this machine real quick. I can reboot it. Anyways, okay. So if you've seen my stuff before, you know that I really love really small little they're called binaries. So I like to make really tiny things and just do generally weird stuff with computers. And files. So I'm gonna just here we go. I don't know how to use this. I never use slides. I use the command line for stuff. So, but yeah. So all right, let's get into it. So who am I? This is I'm you or netspooky on Twitter and GitHub. My website is n0.lol, and I do a lot of things with BugCrowd. Next slide here. So talk outline. It's real simple. We are just going to be going over some file format hacking stuff, some various case studies, use and abuse cases, and different approaches to ELF PE files, and then some further reading resources. So let's just do a little brief overview on file format hacking. So there's been extensive research done into file format hacking. There's been people doing stuff since files have been a thing. People have been messing with making tiny files, putting files into other files. So we got this awesome repo about the smallest possible files, mem/small. Anything that's like a valid file is cataloged here, the smallest possible versions of it. There's also a lot of cool research into stuff like polyglot files, which you may have heard of, chimeras, schizophrenic files, tons of stuff like that. You name it, those kind of things have been endlessly researched. There's a lot of really great research, especially by Anne Albertini. Posted a lot of stuff in POC or GTFO. If you want to see issue 7, article 6, abusing file formats, is a really good primer on a lot of that. And then also this really awesome one I just threw in here because VI Greatech's in the chat. VI Greatech made a Game Boy ROM, NES, PDF, HTML, and zip file polyglot, which is like, I think the most that I've ever seen. It's really awesome. So one second. Keep clicking out of the work window. So if you've done a ThugCrowd challenge before, one of our chat challenges or one of our just general CTF challenges, you may have seen polyglot files before. So this is an example I just wanted to throw in here for file format hacking, just as a background if you've never done it before. This is badge.gif. So in 2018, we did a challenge for DEF CON, for a custom DEF CON badge. And so it was a GIF file where there's a polygon file with a bunch of stuff in it. So there was GIF, a Game Boy ROM, and a zip archive are the main ones to actually look at. But there was like an ELF, there's like a Commodore 64 demo. There's some like JS fuck. There was like a bunch of ASCII art. So if you've ever been and seen this before, there's a lot of files in there, and they're all valid. So if you want to see other ones too, there's an example off the top of my head is the Spider-Man Frozen Elsa challenge from last year, which is a polyglot that was used. It's a YouTube subtitle file with a hidden JPEG in it that you could only see if you downloaded the subtitle file. But so for stuff like the polyglot file, you can create it with a hex editor. Some people use assemblers. There's other tools you can use. I generally use a hex editor just because it's easier for me to map things out. So the internals of this file, just for curiosity's sake, so we have a GIF at the top of the file as offset 000. It's like a very tiny GIF, 28 bytes. There's some random ASCII art, and then there's a Game Boy header, file header that starts at 0x100. And then at the very end of the file is a zip file that contains a text file. And so basically, you go through the process of it. If you go back to this thugcrowd.com/chow/badge.gif, you can go through it yourself. But taking it apart and doing the file forensics, you see that there's a valid GIF at the top there. All the rest of the bytes are ignored. And then there's a zip file at the end of this Game Boy ROM, which is really the base file, because the Game Boy ROM itself doesn't care about anything that happens at above 0x100. So that's just a basic primer on being able to stuff files into themselves and stuff random, put random files around. So why do I talk about this? This leads into binary golf. So binary golf is the practice of crafting the smallest possible binary that still performs a given function. So any file that is super duper tiny, but it still actually works. Whether or not any other tools or software can understand it, all that really matters is the operating system that's running it can understand it and execute it. So these can be created with or without a compiler. I generally don't use a compiler to do these. I basically just use NASM and a hex editor if I have to do any mistakes. You can use like FASM or any other sort of assembler if you want to. I have seen people do binary golfing with GCC. Anonymous, if you're listening, he's definitely made some very tiny things with GCC and some crazy linker scripts, but it's a lot of work to do that, and it's generally a lot easier if you're going to play around with this to use NASM. So what are the use cases for a tiny binary? So there's a lot. You can do basically anything on here. There's anti-debug, anti-forensics. You can prototype exploits and shellcode, AV and detection bypasses, file upload filter bypasses, fuzzing, malware loaders, and fun too, which all the above is pretty fun. So here's some examples here. The top one is Gidra not being able to read an ELF file that I made. There's also strace that I was using to analyze an ELF file that segfaulted because I ran it trying to trace syscalls. There's also some like borked output from readelf, and the very bottom is a completely crashed what's it called, a VM on an ESX host because of a file that I had run that corrupted the VM image. So approaches to binary golf, similar to polyglot files, but basically you start off by examining the binary's file structure. So every binary is going to have headers, it's going to have sections, different parts where data is stored. So you want to really like understand what the actual binary structure looks like. And there's tons of tools for them. There's readelf, there's tons of things for PEs. Basically just being able to understand what are the different components of a binary and what's it called? Being able to like understand how they all fit together. So you can do a lot of this by also analyzing specifications of the binaries, or if there's an RFC or some dev notes, you want to be able to get a bit more understanding about the format. There's also open source parsers for files that you can analyze that will allow you to get a little bit more insight into how those actual parsers look at and understand the file. And so once you get a good handle on that, you can start slowly removing things that you don't need. And so whether that's zeroing out sections or patching, specific parts of the binary that are pointing to different structures, or seeing if you can overwrite certain things, what happens. You can also use a fuzzer to generate small binaries or binaries in general that have certain sections fuzz and then try to run them. Seen a lot of cool tests with that too. And you can also use binary diffing. So if you say you get a regular compiled binary and a stripped binary, you can look at the differences between those and see where the extra sections are that were taken away. And so there's a lot of different tools that come into play, and there's no one right way to do it, but whatever works for you and your workflow is all that really matters. So let's start off with the ones that you may have seen the most. These are ELF64s. So ELF files are binaries that run on Linux. They're executables. So if you run Linux and say have Zoom, Zoom is going to be compiled as an ELF file when it runs on Linux, which notoriously does not have ASLR or a bunch of other things there as well. So ELF64, they have a lot of extra things in them that are not needed. So these include debug symbols. So these are things that a debugger might use to understand more about the file. They could be everything from certain function names and variable names all the way to like the path and the compiler that you use to make the binary. There's a lot of unnecessary sections and headers. GCC likes to put a lot of those in there. They can ruin your day if you aren't doing it right. There's a lot of padding in the binaries too, just lots of zeros that there could be stuff stuffed into. If you ever saw the TikTok that I made of Docker run C, finding code caves or caves where you can put data there's padding, but it's still executable. I did that with the Docker run C binary and backdoored with a Docker image. There's a TikTok with the hit or miss song. There's also a lot of other extra info that's needed by parsing tools like readelf or objdump. So all you really need for a standard ELF binary is an ELF header, a program header, and then code to execute. And so the big important note here is that shared objects and kernel modules require additional parts, and I'll get into those later. So TinyElf files, so there's been prior art to this. So there's muppetlabs.com, this one here, the teensy elf. It's a very small elf file, but it's 32 bits. And so it doesn't run on x64 Linux. Syscall interface is different now, so the code doesn't even work the right way. And it's really cool. I love the way that it was done, but it doesn't work nowadays. So when you're trying to do something in 2020, this is you have to look at it from a modern perspective. So I have a bunch of 64-bit TinyElf examples. So if you go to github.com/netspooky/golf club, I have a lot of my tests in there that you can take a look at the source of and see how I did it. So I updated a lot of them for modern systems. Some of the payloads and other things that are interesting, they also were older shell code or other little snippets, and so I updated those as well for modern systems. So if you are interested in how to make shell code too, that is another big part of this, and you can look at that repo for it as well. And I wrote 3 parts of a blog on binary mangling, as I called it, of how to actually go through the process of this and what I did for the research. One second, let me get the water. So when you're doing ELF golfing, basically, you're going to need to do a few different steps. And so a lot of them have already been figured out, but this is kind of the workflow that I did. So I started by stripping unnecessary headers and sections, which is it's only one bullet point, but that's a very, very large part of it, is figuring out what isn't needed. The other big thing here, which you can go and look at my blog post if you want more information about it, but overlaying program headers with ELF headers, or overlaying any sort of headers in general, significantly makes the code or the headers smaller. But what you're doing is reusing certain values from other headers at the same time. So there's this specific binary here. There are parts of it in the thing that's called SIA in the little label. That's if you see my mouse, like almost halfway down. This is not only is it code, it's part of the ELF header and the program header at the same time. So it's parsed 3 different times for the kernel when this executes. So this is a very, very important piece of this too, is if you can figure out ways to point headers elsewhere into the file and move them around, then you can overlay them and create, put multiple values and use them for the same purpose. And so this takes a lot of time and energy to do, to figure out. But once you do, you have a really tiny way to go, or a tiny template to work with. So the other big thing about this too for binaries is storing code and other data in unused sections of the header. So headers, even though they have these structures that might need to be a certain length or whatever, they might still not actually care about some of the values. There's some of the things like flags are only using the last 3 bits of the byte, right? Or however big the size of it is. And so that means that you can, as long as those 3 bits are set correctly for executable, read-write permissions, those you're still able to execute it, but you can also use the first, let's say, like 5 bits of it for some other piece of code or data. So that part is also pretty complicated. That's, you can read my blog more about it too. But reusing values from the header, those are all parts of it that are really important. Short jumps to locations within the header. So if you see SIA and reeb and start as labels in here, these are all these little jumps here are just jumping around the header because I don't have enough space to put all the code that I want, but I have a little bit of space, and short jumps are only 2 bytes, and you can use those. So if you have 4 bytes, you can still do something like the syscall command or move al 0x a9 and then jump somewhere. So being able to do that kind of math and figuring out where you can actually put code and how you can jump to and from it is important, but there's a lot of cool resources that I have in some of my blogs. The other big one is loading the binary at 0x1 and then a bunch of zeros. Basically, that's used so that the E entry for ELF header and P type for program header matches, and it's loading at a very, it's still within the 64-bit address space, but it's pretty high. So next is, okay, so I saw this the other day, golf.so. So there's a recent CTF challenge to create a shared object that's under 1024 bytes that also pops a shell. So there's a link here. I'm going to make the slides available like shortly after my talk. But so shared objects are really cool. They're interesting because they have a lot more strict checking. So if you do something like, say, what I did up here, where the start is at 0x04 in the ELF header, you'll get messages like this that say that you can't load something because it actually checks whether or not these values of where all the other jumps and stuff are in start actually are. So it's actually invalid. This whole thing is a lot more difficult to do the techniques that I had. So shout outs to the people who actually solved this. This is a really small shared object. Also, yeah, it was invoked using LD preload. So golf.so, so what this is the source code for it. And what they did basically here was determining the needed sections. So they have the this dynamic sections with DP, string tab, init, and symtab, and they put these in here, and it's still overlaid with the program header and the ELF header, and the dynamic section is also overlaid within the program header too, and then their code is right there. I tried to make this smaller, but it's very packed. This is a very, very good version of this code here. They use NASM, though, the same to create the final binary, and the resulting file was 185 bytes. So look at a lot of ELF here. ELF is more my specialty, but I started to work with PE files, and they were a bit different than what I was used to. Similar sort of, I guess, techniques, but I'm not a Windows person at all. So if anybody who is one in here and has done stuff like this, forgive me. But this PE, studying PEs is different because there's different versions of Windows. So each version of it may change the spec slightly. So there is been prior work on this, and there was changes between Windows 2000 to XP to Vista, etc. And so none of those worked on Windows 10. So I had looked for resources for modern Windows systems, and I found that PE files must be greater than or equal to 268 bytes for whatever reason on Windows 7 and 10. And so I saw some examples. Korkami or Njabertini had done a lot of work with PE files. This RCX/TinyPE repo was really cool. It actually gave me a framework to look at first to see how somebody actually would make a tiny PE. Because I think they use Visual Studio, which I don't know how to use. So I don't know how they did it, but I had translated to NASM and worked from there. And so what I had come up with was a tiny PE that had done similar work to what like my ELF files did, but I used similar techniques, but there's a slightly different thing with PE files. So exploring code caves is really important. So the same things we did before, we're putting little bits of code in like a couple of bytes in values in the header is really useful. So I identified some different caves that I can put stuff in. So there's like 12 bytes at 0xc to 0x18 and stuff like that. So I identified a bunch of them by analyzing all the different headers and figuring out which ones weren't used, and then put my code in there after the overlay. And so I use short jumps again to hop around the header. And you can use a fuzzer to check for these, but my process was really manual because I was trying to figure it out myself. And so a lot of these headers that are in here aren't actually used, which is pretty cool. So you can, even though they're big and they're annoying looking, you can still put code in them. So what my PLC binary did was launch calc.exe. So I used the PEB to WinExec technique to launch calc.exe. But the shellcode for it that I found was a bit longer than could fit into the actual binary. It was like 310 bytes rather than 268. So I was like, all right, I'm gonna shrink this payload down even more. So I optimized more of the shellcode by writing it like a little bit more optimization. And then I manually patched and put stuff in the header. So if you see the side here, this is all the header being created. So you can read the PE Mangle write-up that I did that explains it a bit better. But these are a ton of jumps within the PE header. So it looks really, really crazy now that I'm looking at it and trying to explain it. But there's a lot of these things are overlaid, and there's like multiple times where it's parsed like 3 or 4 different ways while it's executing. So I had basically done, took these caves here and basically just put all these jump labels into here and put code in there and worked out the actual flow before I get to the very last line of this thing on the side, jump 6. That is the actual start of the code section. So there's a ton of code that happens to set up reading the PEB, to read kernel32.dll in this. But yeah, if you want to read more about this, there's a big write-up I did recently. And yeah, so cool thing about this though, so you see all this, you see all these different, pieces of code, and you are able to pick where each individual byte is. And so what you can do with it is defeat detection. So there's a lot of detections for small binaries and weird payloads and stuff like that. And so TinyPE is very, very well known. This technique is not new. And so there's detections for them that are on VirusTotal. There's tons of them that run Yara rules for them. And so I was made aware of one of them that was put out there because someone had shared a Yara rule, they had written about it, that had caught this on VirusTotal. And so what I tried to do was see if I could actually defeat this. So what I ended up doing was, if you see the little circled red circle there, I changed one bit within this. This used to be a 0, and now it's just a 0, 1. So one bit, and I was able to actually bypass the Yara rule because of what it checked. Because even though it's very small and there's a lot of stuff that's going to be in the same places, there's still extra data that you can put in there. And so I rewrote the Yara rule to actually make it catch this, but this is an example of actually evading this detection. So if this detection has been in place for a long time, this would have still been able to defeat it. And there are still ways to actually get around this detection, but yeah, this was the this is like an example of being able to control each individual byte. And also shout out to Shell, because he had actually done a ton of work on fuzzing VT detection engines, which are really funny. I don't have a link to it directly right now. Shell probably can post it in the chat, but very good write-up on how fragile antivirus stuff still is. And so I'm getting towards the end of the talk here. So lessons learned. You don't need huge bloated software to run binary programs in 2020. File parsers are generally pretty lazy, and they only really care about a few things to consider a file valid, whether it's a tool that parses stuff or your operating system's kernel. Most debuggers and binary parsers really do suck at understanding minified binaries. Like there's a couple of binaries that I've found that can't be opened in anything but redRA2, and redRA2 struggles to open it. I've also gotten passes so that not even redRA2 can open it. But yeah, you can make files that basically like no program can read, that only the operating system can understand, which is pretty cool, because if you're writing anything that's wants to be secret, you might want to have something really small that nobody can read. But even with a tiny binary, even with very small surface area to actually move bytes around, if you wanted to throw in extra bytes to defeat hash analysis or something, you can still bypass detections. It's definitely possible. You just got to be creative and see, where you can move data around. And binary golfing can give you complete control over every single byte in your file. So if you like that kind of control over something, definitely a fun thing to play with. And you too can have a hole-in-one. So last is other resources. So redRA2 is great for debugging weird stuff. It's probably the best thing, in my opinion, for debugging weird stuff. There's still issues with how it actually works as a debugger, but as far as being able to understand certain things, it's my go-to for why is this file weird and what is wrong with it. If you want to look up Core Kami's stuff, amazing work. Angel Bertini has done making files more accessible to people. File formats.archiveteam.org is another amazing site where they have cataloged tons of file formats, because they're the archive team for archive.org, and they are trying to save all the files. And lastly, I did a stream a few months ago called Intro to Assembly Optimization, and it talks a lot about this sort of techniques for actually optimizing your assembly code and making it even smaller and smaller, to making shell code basically. And so yeah, that's pretty much it for this. I'm going to stop sharing real quick. I kind of breezed through it really fast because I was started a bit late, but yeah,